Hello and welcome to this poster presentation. My name is Fredrik Ljungberg and I'm presenting a poster entitled Ship Modeling for Estimation and Control, which is also the title of my PhD project within LINK-SIC. The ambition with this poster is to give a summarizing overview of what my research has been about. The ship models are often expressed using what are called the equations of motion. I will not go into any details regarding these, but it is important to note that mu, which constitutes the ship's velocity, appears with subscripts q and r, which signifies relative velocities with respect to air and water, respectively. It is the motions of these two surrounding media which are the main sources of process disturbances for ships. The model is nonlinear because the superimposed forces are often described using quadratic functions with absolute values. So to be able to suggest parameter estimators for general ship models, we make the following definition. A second-order modulus function is a function which can be expressed as a matrix whose elements are quadratic terms, possibly with absolute values, multiplied with a parameter vector. Based on this definition, we can consider a state space system using standard control notation. Notably, the state evolves based on a second-order modulus function, so this system formulation includes, for example, the model to the left. In that case, the disturbance signal V corresponds to wind or ocean currents, and the matrix R, the rotation matrix between a global and ship fixed reference frame. In addition to this, we consider a predictor model and an instrumental variable estimator. The objective that I worked with during the first 3 years was to find an accurate parameter estimator for models in this setup. Three disturbances, E, V, and W, the non-additive disturbance denoted by V is the most challenging one to deal with. The parameter estimators were thereby developed with increasing levels of difficulty based on the character of V. To begin with, it was assumed that V had zero mean. The physical interpretation of this is that there is bursty wind or currents without any static deterministic components. In this case, a two-step solution is sufficient where the data collection experiments are performed with excitation offset and the instrument matrix is forced to have zero mean. In a second step, we considered V with non-zero mean and a constant matrix R. A physical interpretation for this is a ship moving with fixed orientation in an environment where the wind or current has a constant component. In this case, it is hard to find a consistent estimator unless V is measured. This might sound quite limiting, but it is actually quite common that ships are equipped with sensors for measuring wind speed and direction. It is, however, not so common to have sensors for ocean currents. In the final step, we considered V with non-zero mean and a time-varying matrix R. In this case, it is possible to get a consistent parameter estimator if R is measured and included in the predictor together with some extra parameters. In this case, we're estimating the first-order moment of V alongside the model parameters, and in addition to giving consistency, this gives information about the environmental disturbances, which can be valuable by itself. A second sub-project has been about the design of data collection experiments. Here the goal is to find an input signal which makes estimator sensitive with respect to the parameters. In general, this is a non-convex problem and solving it would require a good initial guess, which is not available. So our approach to solve the experiment design problem is quite simple, and the keyword is improved design instead of optimal design. We consider a finite set of input signals, which correspond to standard excitation maneuvers as depicted in the figure above, and we then estimate the information gained from each such sub-experiment and solve for the best mix of candidate signals. That is, we find out how much of the total experiment time that should be spent performing each basic maneuver. Then, in a second step, we solve a lattice-based motion planning problem where the candidate signals are used to form motion primitives. And here the time ranges between different maneuvers that were determined in the first step are taken into account by adding motion primitive counters to the state vector. So in this way, we're able to plan experiments which give informative data in a time-efficient manner, while at the same time environmental constraints such as islands are avoided. And if you have any questions, you're most welcome to contact me. Thank you very much for your attention.